Welcome to G Fun Facts Online. Today, we're diving deep, thousands of meters below the sun-drenched surface of the Indian Ocean, into a realm of crushing pressure and inky blackness. Here, scattered across silent, vast plains, lies a treasure that could redefine India's future. We're not talking about pirate gold. We're talking about unremarkable, potato-sized rocks that hold the key to our entire technological world. These are polymetallic nodules, and India is on an audacious, multi-billion-dollar hunt for them. This quest is spearheaded by the ambitious Deep Ocean Mission, a clear statement that India is ready to join the elite club of nations capable of harnessing the immense wealth of the deep sea. At the heart of this endeavor is the pursuit of three types of mineral deposits: polymetallic nodules, polymetallic sulfides, and cobalt-rich ferromanganese crusts. These aren't just rocks. They are compact storehouses of critical metals like cobalt, nickel, copper, and manganese. Think about the device you're listening to this on, the battery in an electric car, the components of a solar panel. All of them depend on these metals, and demand is soaring as the world pivots towards a green economy. The main targets, polymetallic nodules, are potato-sized concretions that lie on the abyssal plains at depths of 4,000 to 6,000 meters. They form over millions of years as metals in the seawater slowly precipitate and build up around a tiny core, like a piece of shell or a shark's tooth. They grow at a rate of just a few millimeters per million years. In the area of the central Indian Ocean Basin, allocated to India by the International Seabed Authority, an area of 75,000 square kilometers, it's estimated there are 380 million tons of these nodules. This staggering amount contains roughly 92 million tons of manganese, 4.7 million tons of nickel, 4.3 million tons of copper, and over 500,000 tons of cobalt. To put that in perspective, the cobalt concentration here is about 100 times more enriched than in ore deposits on land. Then there are polymetallic sulfides. Unlike the slow-growing nodules, these are formed rapidly at hydrothermal vents along mid-oceanic ridges. Superheated mineral-rich water, reaching up to 400 degrees Celsius, erupts from the Earth's crust and hits the cold seawater, causing dissolved metals to precipitate and form massive sulfide deposits. These are underwater treasure chests filled with copper, iron, zinc, and even silver and gold. India holds 2 exploration contracts for these sulfides in the Indian Ocean. The third target is cobalt-rich ferromanganese crusts. These form like pavements over the rocky surfaces of underwater mountains or seamounts. They also grow incredibly slowly and are particularly rich in cobalt, titanium, platinum, and other rare earth elements. Securing a domestic supply of these resources would be a game-changer for India, reducing its heavy import dependency, bolstering its Make in India initiative, and securing its energy needs for the next century. This isn't a new idea. India's journey into the deep sea began decades ago. As far back as 1981, a research vessel collected nodules from the Indian Ocean, earning India the status of a pioneer investor in 1987. But the Deep Ocean Mission, officially launched in 2021, marks a new era. With a budget of approximately $480 million for its first 5 years, it's a comprehensive national program designed to develop the technologies for exploring and sustainably using the ocean's resources. Prime Minister Narendra Modi has called it a modern-day Samudra Manthan, a powerful metaphor from Hindu mythology signifying the churning of the ocean to find the nectar of immortality. In this case, the nectar is the resources that will secure India's future. The mission has 6 major components, but the cornerstone is the development of indigenous technology for deep-sea mining and underwater vehicles. Venturing 6,000 meters deep is arguably more challenging than exploring outer space. The pressure can exceed 600 times that at the surface. The salt water is corrosive, and the environment is one of complete darkness and freezing temperatures. To conquer this abyss, India's National Institute of Ocean Technology, or NIOT, is developing a suite of incredible machines. The centerpiece of the manned program is the MATSYA 6000. The name MATSYA means fish in Sanskrit. This is a crewed submersible, designed to carry 3 aquanauts to a depth of 6,000 meters. Its core is a 2.1-meter diameter personnel sphere made of a specialized titanium alloy developed with help from the Indian Space Research Organization. This sphere is built to withstand pressures of 600 bars. With its own life support, navigation, robotic arms, and cameras, it will have an operational endurance of 12 hours. Successful development will place India in an elite group of nations, alongside the US, Russia, China, France, and Japan, with the capability for manned deep-sea missions. The first manned mission is expected by the end of 2026. While MATSYA 6000 will be the eyes and ears, the heavy lifting of mining will be done by unmanned robots known as the Varaha mining system. Imagine a crawler-based machine moving along the seabed. It collects the nodules, crushes them, mixes them with seawater to form a slurry, and then pumps that slurry up a 6-kilometer-long flexible riser system to a mothership on the surface. NIOT has already had major successes. In 2022, a prototype named Varaha 1 successfully performed locomotion trials at a staggering depth of 270 meters in the central Indian Ocean, crawling for over 100 meters on the seafloor. More recently, an advanced version, Varaha 3, was tested in the Andaman Sea, successfully collecting nodules on a rocky, uneven terrain. These successes are a massive leap for India's technological prowess. But this new frontier isn't just a tech challenge. It's a legal and geopolitical chessboard. The United Nations Convention on the Law of the Sea, or UNCLOS, declares the seabed beyond national jurisdiction as the common heritage of mankind. No single nation can own it. An organization called the International Seabed Authority, or ISA, was set up to manage these resources for the benefit of all humanity. Any country or company wanting to explore or mine must get a contract from the ISA. India has been a proactive player, currently holding 3 exploration contracts, 1 for nodules and 2 for sulfides. This is also a geopolitical race. The seabed is prime real estate. China holds 5 exploration licenses and Russia has 4. India's push is a strategic move to project its power and ensure it doesn't get left behind. Now, we come to the most critical question. Amidst the promise of this underwater El Dorado, there's a growing chorus of concern from scientists about the unseen costs. The deep ocean is a fragile, biodiverse, and largely unexplored ecosystem. The environmental risks of deep-sea mining are profound. The most direct impact is the complete destruction of the seafloor habitat. Mining machines will essentially strip mine the seabed, wiping out entire communities of organisms that have evolved over millions of years. Many of these species are found nowhere else on Earth. Given the slow-motion pace of life in the deep, this damage would be irreversible on human timescales. A study of a test mining site in the Pacific, 44 years after the disturbance, found biodiversity was still significantly lower than in undisturbed areas. Then there are the sediment plumes. Mining will kick up vast clouds of fine sediment that can drift for hundreds of kilometers, smothering marine life, clogging the feeding systems of filter feeders, and disrupting the entire food web. Add to this the noise and light pollution from machinery in a naturally dark and silent world, which can disrupt animals that rely on sound and bioluminescence to communicate, navigate, and hunt. Finally, the deep sea is a massive carbon sink. Mining could disturb these sediments and potentially release stored carbon, which would only worsen climate change. Faced with this, many scientists and environmental groups are calling for a precautionary pause or a moratorium on all deep-sea mining until the risks are better understood. The Indian government states it is committed to balancing exploitation with environmental protection, conducting baseline studies and preparing environmental impact statements. But the question remains whether regulations can truly protect these unique ecosystems. So India stands at a crossroads. On one hand, the Deep Ocean Mission could unlock a new era of economic growth, technological self-reliance, and strategic autonomy. It could bolster the blue economy, create jobs, and reduce India's dependence on other nations for critical minerals. On the other hand, the path to this underwater treasure is fraught with the risk of causing an environmental catastrophe we might regret for generations. As the great churning of the ocean begins, what will emerge from the depths? A bounty of prosperity, or a legacy of destruction? The answer will depend on whether we prioritize short-term gain or the long-term health of our planet's final frontier. The world is watching,